Okay, we're going to continue now with some other nucleophilic addition elimination reactions involving acid chlorides. So far what you've seen are methods to convert acid chlorides to the other carboxylic acid derivatives. But this nucleophilic addition elimination reaction is not just useful for that. It can actually produce a whole host of new organic compounds in addition to acyl derivatives using nucleophilic addition eliminations. And the first reaction we're going to look at is the reaction with an organometallic. And you know organometallics by now. We make Grignard reagents. Here's one example, a phenylmagnesium bromide. But this would also apply to organolithium compounds. I'm going to start off with this acid chloride of acetic acid. This would be called acetyl chloride. Let's just review very quickly how we would make that. We would take acetic acid, which looks like that, and we would treat it with thionyl chloride. So if we wanted to make thionyl chloride from a carboxylic acid, that's how we would do it. What about this organometallic, this Grignard reagent that we're going to react it with? This is phenylmagnesium bromide. Where would that have come from? Well, that would have come from bromobenzene, which we treat with magnesium metal in the presence of ether. And again, for the Grignard reaction, stating the ether solvent is absolutely critical because it doesn't work in other solvents. The bromobenzene itself we could have prepared from benzene using our standard bromination conditions, electrophilic aromatic substitution bromination conditions, bromine in the presence of iron tribromide. So that's where those things are coming from. We've got now our acid chloride, we've got our phenylmagnesium bromide. What's this reaction going to look like? Well, remember, this is an organometallic, so these two electrons of this carbon-metal bond largely reside with carbon, and we can take those two electrons and use them as nucleophilic electrons in this way. Here we're basically doing a nucleophilic addition. The Grignard reagent or the organolithium is the nucleophile. There's our electrophile. We must simultaneously move those pi electrons up there, otherwise we'd be in violation of the octet rule. So we'll go ahead and do that. And what's going to happen is, of course, we're going to form a tetrahedral intermediate, as we always do in these nucleophilic addition elimination reactions. This is what the tetrahedral intermediate looks like. There's my methyl group, there's my phenyl group of my Grignard reagent that came in. What happened to the magnesium bromide? Now that's the spectator cation, so it's just going to be floating around adjacent at this moment to the oxygen, because that's where the anion is, the anionic charge. Okay, there's my tetrahedral intermediate. If you look carefully at it, it's very clear where this has to go. We're going to reform the carbon-oxygen pi bond, which is always going to be the first choice for tetrahedral intermediates like this if it's a possibility. And in this case, it certainly is because they have an excellent leaving group. Only one leaving group. The phenyl group's not a leaving group. The methyl group's not a leaving group. There's only one choice here. We're going to lose the good leaving group. And what does that give us? That gives us, interestingly, a ketone. This is a methyl-phenyl ketone. Well, you might expect the reaction would end there, and that would be consistent with the other nucleophilic addition elimination reactions we've seen so far, but it probably doesn't end there. Highly unlikely that it would end there. And that's because as this ketone is forming, there's still going to be some of this Grignard reagent around. Even if I've only added one equivalent of Grignard reagent, which means the same number of moles of this as this reaction doesn't take place like that. It takes place over time. The ketone is formed over time, and it's formed in the presence of Grignard reagent. For that reason, we know that Grignard reagents, organometallics, in general, react with aldehydes and ketones, and that's a ketone. So the reaction is going to continue. The reaction is absolutely going to continue. This is a complication unless we use an excess of this Grignard reagent and just accept that there's no chance of stopping the Grignard reagent from reacting with the ketone as it forms anyway. So let's just go ahead and use two equivalents, which means an excess of the Grignard reagent, so that we can finish the job and it's not messy. We don't have a collection of products, we just have one product at the end. That's the way we would run the reaction. So that second equivalent of Grignard reagent is just going to come in and it's going to add to the ketone. This is again a nucleophilic addition. In this case, there's no chance for an elimination. So when we talked about nucleophilic addition reactions to aldehydes and ketones, first of all, when we're using an organometallic, it's probably not reversible, and we've talked about that. This is an irreversible reaction, so we can go ahead and change that reversible arrow to an irreversible one. But secondly, when we talked about nucleophilic addition to aldehydes and ketones using things like organometallics, we didn't talk about it in the context of a nucleophilic addition elimination sequence, because once you've done the addition, there is no elimination. That's possible. There's no leaving groups here. The phenyl's not a leaving group there or there, and the methyl's not a leaving group there. So the bottom line is, aldehydes and ketones do nucleophilic additions without the elimination piece, whereas acid chlorides and anhydrides and maybe esters on occasion will do a nucleophilic addition elimination sequence. Well, what happens is the thing just sits here as the alkoxide. Our counter cation is now floating around here still. And so it's just sitting there as the alkoxide anion until we do a workup. In a separate second step, we're going to use H2O, H3O+, in order to produce the corresponding alcohol. This now becomes a very interesting and very clever synthesis of alcohols. Starting with an acid chloride, we can add 2 equivalents of an organolithium or a Grignard reagent in order to produce the corresponding alcohol. Let's look at another example of this to make sure that we get it, we understand what's going on here. I've got butanoyl chloride here, the acid chloride of a 4-carbon carboxylic acid, the acid chloride of butanoic acid. And what I'm going to do is I'm going to go ahead and react it with an excess of the corresponding methyl lithium. So I could say 2 equivalents here, or I could say excess, anything along those lines would indicate I know what I'm doing. What's going to happen, of course, is that the nucleophilic electrons of that organometallic bond are going to attack the carbonyl. There's my new methyl group right there. I've only got 1 leaving group on board, but it is a good leaving group, so there will be an elimination component now. There's the nucleophilic addition. Here's the elimination of the tetrahedral intermediate. Oops. To give me a ketone initially, but that ketone is just an intermediate because it's going to go ahead and react with another equivalent, the second equivalent of my methyl lithium, to give me another nucleophilic addition, but this time no elimination. There's my 2 methyls which are on board now. No elimination because there's no leaving group, so in a separate second step, when I come in with H2O, H3O+, I can produce the corresponding alcohol, which is again a tertiary alcohol. This is really, really useful. Let's say, for example, that I started with benzoic acid, and I wanted to know how could I possibly synthesize this exotic triphenylmethanol molecule. Look at that. It looks big and bulky, almost like it's too bulky to form. But remember, these carbon-carbon bonds can rotate. These phenyl groups don't have to be lying flat like my drawing indicates. They can sort of be moving out of each other's way. This is really a real molecule. Triphenylmethanol exists. How can you make it? Well, you can make it from the corresponding carboxylic acid, benzoic acid, and here's how you would do it. Actually, before I show you how to do it, why don't you turn the video off and try to do it yourself, and turn it back on in a minute and I'll show you how to do it. Okay, so I hope you had some success, but whether or not you did, let's look at the synthesis. We're going to start with benzoic acid and somehow produce this triphenylmethanol. Here we go. Take your benzoic acid and convert it into a carboxylic acid derivative that can react with a lot of different things, namely an acid chloride. Treat it with thionyl chloride to produce the corresponding acid chloride. And now recognize that if you treat it with an organometallic, the organometallic will add twice. Once to form the ketone, we've seen 2 examples of it, and then once the ketone is formed, the organometallic adds again to give an alcohol. Well, we're trying to make an alcohol, and lo and behold, it looks like we've got to add in 2 additional phenyl groups to get to the one we want. So, all that we have to do is, in our first step, add 2 equivalents of either a phenyllithium or a phenyl Grignard, 2 equivalents. And then in the second step, H2O, H3O plus, to quench the alkoxide that will form, and that will give us our desired alcohol. The sequence of steps, the mechanism for the reaction follows exactly the last 2 examples I gave you. So if you don't see that clearly, stop the video now and go ahead and draw out the mechanism. You can go back and look at the prior 2 mechanisms I showed you. It will be exactly the same. Remember, the first equivalent will form a tetrahedral intermediate, which will lose chloride anion to give you a ketone. The intermediate ketone you should have in your mechanism, if you're drawing it out, would be this diphenyl ketone right here. So that would be an intermediate ketone. Then the second equivalent of the phenyl magnesium chloride will come in to give the alkoxide. After protonation, you get that alcohol right there. So there you have it. Acid chlorides will go all the way to the tertiary alcohol when you react them with 2 equivalents of a Grignard. Well, that's not the only other interesting reaction that acid chlorides will do. In fact, there's another one which will produce the primary alcohol. We just showed how to make the tertiary alcohol from an acid chloride. If we react an acid chloride with a metal hydride, like lithium aluminum hydride, we can get it to go to the primary alcohol. This is what lithium aluminum hydride looks like. You've seen it before. And I just want you to know that it is essentially a source of hydride. Hydride is a hydrogen with 2 electrons and a negative charge. Now, hydride never exists in solution as such, but it is delivered as hydride. And this aluminum hydride species right here is the one that will deliver hydride. So let's go ahead and look at the reaction and see how it works. We're going to start with acetyl chloride, that's the acid chloride of acetic acid. And we're going to go ahead and react it with lithium aluminum hydride. I've redrawn it here. The aeroformalism would be the following. Hydrogen with the 2 electrons will be hydride and will be delivered as a nucleophilic species to the electrophilic carbon of the acid chloride. Of course, there must also be breaking of the pi bond in order to avoid a violation of the octet rule. And we're going to form a tetrahedral intermediate. Here it is. I got my CH3, which is now attached to this hydride. CH3 is attached to the tetrahedral carbon, which is attached to the hydride. There's the new bond that formed when the hydride electrons came in. This is my tetrahedral intermediate. The carbon-oxygen bond can reform, and I can have an elimination component here simply because I have a good leaving group. And when that happens, now I've got a methyl on that side, a carbonyl on that side, and a hydrogen on that side, the chloride anion leaving group. This is acetaldehyde. This is an aldehyde. What we know about aluminum hydride species is that they react with ketones and aldehydes just as well as they react with acid chlorides. And that will in fact happen. Lithium aluminum hydride is a powerful hydride donor, and it can give up to 4 hydride equivalents. So this is just going to continue. I'm going to write lithium aluminum hydride here, and I'm going to show hydride coming in and attacking the aldehyde. Of course, the hydride is not floating around in solution like that. It would be delivered in much the same way I showed hydride adding here. It would be delivered to the aldehyde in order to produce a new tetrahedral intermediate. This new tetrahedral intermediate now has 2 bonds to hydrogen. One came in the first step, the other came in this last step. This tetrahedral intermediate, however, cannot eliminate. Similar to something we just saw with the addition of organometallics, we've added 2 equivalents of hydride, and now this intermediate is stuck. There is no leaving group. Hydride is not a leaving group. Methide is not a leaving group. Those aren't going anywhere. This thing is stuck until, in a separate second step, we hit it with water and H3O+ in order to produce the corresponding alcohol, which in this case is just ethanol. A primary alcohol. So, the acid chloride can be converted to a tertiary alcohol by adding an organometallic, like a Grignard or an organolithium. 2 equivalents will add. Or it can be converted to a primary alcohol using a metal hydride like a lithium aluminum hydride. Let's go ahead and show another example of this. It's very interesting, actually. We have a way now to take a carboxylic acid, I'm going to start with butanoic acid here, and convert it into the corresponding alcohol. If you look carefully at that reaction, it is undeniably a reduction. So we could write reduction, RED, in brackets. This is a reduction reaction because the number of bonds to oxygen is certainly decreasing, 3 to 1, and the number of bonds to hydrogen at this carbon is increasing, 0 to 2. Both of those things define this as a reduction reaction. How can we get it to work? Well, we'll use the sequence we just learned. Treating this carboxylic acid with thionyl chloride, we'll convert it into the corresponding acid chloride, and then treating it with, in the first step, lithium aluminum hydride, and in the second step, H2O, H3O+, will allow 2 hydride equivalents to add, first to form the aldehyde as an intermediate, and second, the addition to the aldehyde to give an alkoxide anion, which is then protonated to give the alcohol. If you want to go ahead and draw out the mechanism for this reaction, right here, the last step, the acid chloride to the alcohol, recognize that an intermediate species that should be in your mechanism is the corresponding aldehyde. That's formed first, and it reacts with a second equivalent of hydride to give you the alcohol. So, very, very interesting. We can take acid chlorides, convert them into alcohols, tertiary alcohols or primary alcohols. Now, let's just say, for sake of argument, that you would like to be able to stop this reaction. I'm talking about the metal hydride reaction. You'd like to be able to stop it at the aldehyde stage. You'd like to be able to reduce the acid chloride not all the way to the alcohol, but just to the aldehyde. Can it be done? Well, if the answer were no, I wouldn't have brought it up. So you can guess that the answer is yes. And actually, there's 2 ways to do it. The first is called a Rosenmund reduction. It's an old reaction. It basically utilizes hydrogenation conditions. You can take an acid chloride and treat it with hydrogen gas in the presence of a transition metal catalyst, palladium. That should look like a familiar set of conditions for you. Those would have been the conditions we've used in the past to do things like hydrogenate an alkene or an alkyne all the way to the corresponding alkane. Turns out, because the acid chloride is so reactive, you can actually use those conditions to reduce an acid chloride. But it's so reactive that that alone won't work. It would probably over-reduce all the way to the alcohol. What you need to do is to add a poison. And the poison that we add in this particular Rosenmund reduction is really a witch's brew, which contains something like barium sulfate and, more importantly, quinoline. And that's what quinoline looks like. So what you can do on paper is simply write H2 palladium quinoline, or you can draw out the structure for quinoline, whatever you like. That tells me that you recognize this is a Rosenmund reduction. You're going to need Rosenmund reduction conditions, and under those acid, or I should say poisoned catalyst conditions, the reaction will progress to that aldehyde and stop there. So that's a very nice way to convert a carboxylic acid chloride into the corresponding aldehyde. A reduction, but not the full reduction all the way to the alcohol. There's a second way to do the same thing. This one uses an aluminum hydride, a metal hydride. There it is, aluminum hydride. But it's not lithium aluminum hydride, in which case the aluminum has got 4 bonds to hydrogen. It's only got 1 bond to hydrogen, and the other 3 bonds are to this very bulky T-butoxy group. So this is a tri, because there's 3 of them, tri-T-butoxy aluminum hydride. The lithium is the cation still, so it's a lithium tri-T-butoxy aluminum hydride. That's a mouthful to say. Again, it's a bit the same as the Rosenmund reduction in the sense that you're not adding a poison to the catalyst, but instead you're adding big bulky groups which really slow this thing down. There's only 1 aluminum hydride left, 1 bond between aluminum and hydrogen, and the rest of it's so bulky that this particular aluminum hydride will allow you to go from the chloride to the aldehyde and stop there. 2 ways to do it. 2 ways to get from the acid chloride to the aldehyde, and then the reaction stops. Well, this is all very, very useful because it allows us to do a lot of new syntheses. Let's just say, for example, that we wanted to go from the carboxylic acid to the corresponding aldehyde. Well, there's probably a couple different ways to do this now. But in tune with what we just learned, if you were to treat this carboxylic acid with thionyl chloride, that would give you the corresponding acid chloride. And you could then take that acid chloride and convert it to the corresponding aldehyde using either a Rosenmund reduction or the lithium tri-T-butoxy aluminum hydride. Both of those will allow you to stop at the aldehyde stage. Okay, so we've looked at some more reactions of acid chlorides, reactions that give rise to alcohols and or even an aldehyde. What I'd like to do now is I'd like to start looking at some reactions of some of the other carboxylic acid derivatives. We won't spend nearly as much time talking about them because of everything we've already mentioned. The carboxylic acid chlorides are the most reactive and therefore the most useful to run a variety of reactions. But we should look at a few reactions of some of those other acid derivatives. So for example, let's start with anhydrides. There's really only one thing I want to tell you here, other than a quick review of the structure of an anhydride. We don't see a lot of them, or at least we haven't seen a lot of them yet. So the structure of an anhydride looks like this. You've got 2 carbonyls sandwiched together, or tied together, if you will, by that central oxygen. It looks a bit like an ester on this side. There's the ester appearance. And with that second carbonyl, though, it becomes an anhydride. The one thing I want to tell you is that it is possible, as I think I already mentioned, that you can produce anhydrides simply by condensing, bringing 2 carboxylic acids together. And if you do that in a molecule like this, which is an aromatic ring in which I've got 2 carboxylic acids attached in an ortho position, this would be called orthophthalic acid, which is just a generic or trivial name. If you've got those 2 carboxylic acids right next to each other on the same molecule as we do in this case, then the reaction becomes a little bit easier. I told you before that this is one that requires fairly harsh reaction conditions. It literally is a dehydration reaction. You've got to heat this thing up in order that you can dehydrate it, drive off water. The reaction no doubt involves a nucleophilic addition elimination sequence, And if you worked through the mechanism or tried to work through the mechanism, you'd see that there's no good leaving group once you get to the tetrahedral intermediate, and that's why the harsh reaction conditions are required. You're trying to drive off a bad leaving group. But you can do it, especially in these cases where you don't have anything else on the molecule that's fragile, and the two carboxylic acids are stuck right next to each other. There's the mechanism. If you're working at high enough temperatures, then, which means over 100 degrees, then water is going to be a gas at those temperatures, and it's driven off, and therefore the reaction's not reversible. And that's certainly a big part of the reason that this reaction can be successful. This particular compound is well known. This is called phthalic anhydride. So there are other ways to make anhydrides other than this brute force method, but for simple compounds like this one, the brute force method works reasonably well. That's all I wanted to say about anhydrides. Let's talk a little bit about esters. Once again, the structure of an ester looks like that. And as I told you before, esters are very pleasant smelling, fragrant smelling compounds. If you were in the fragrance industry, let's say you worked for a fragrance company, which a lot of organic chemists do, you would be very, very interested in their odor, and you would be very interested in tweaking their odor. And it turns out that any small structural change you make to an ester is going to impact its physical and chemical properties, including its odor. So, for example, there is a reaction called a transesterification, which allows you to do just that. It allows you to tweak the structure ever so gently in order to change it and ultimately change the fragrance associated with the compound. So I'm going to just go ahead and start off with this particular ester. This is the methyl ester of benzoic acid, or methyl benzoate. And I'm going to say, well, what if I wanted to change its structure in order to change its fragrance, and I wanted to convert that methyl group into an ethyl group? How could I do that? Now, that's not a very big change, but it will, in fact, impact its physical and chemical properties, including its fragrance. So, how to do it? Well, the easiest way to do that would be through a transesterification. What you do is you take advantage of the fact that you're adding, or at least you're going to add, an ethoxy group, which is no doubt going to come from ethanol. And you basically treat this to Fischer esterification type conditions, which means you're going to have an excess of the new alcohol, which is going to give you the new transesterified structure, an excess of that alcohol in the presence of an acid catalyst. This is really just like a Fischer esterification, except we're not starting with a carboxylic acid, we're starting with an ester. But mechanistically, it would proceed in exactly the same way. The transesterification, excess of the alcohol under acidic conditions. It turns out you can effect the same change under basic conditions. That is, instead of adding a whole bunch of ethanol under acidic conditions, you can add ethanol under basic conditions, which is going to give you ethoxide anion. Here you would still have ethanol as your solvent. You'd always choose the correct solvent. In this case, ethanol was the solvent. We're drizzling in a little bit of acid catalyst. Here, ethoxide anion is the basic or nucleophilic component, which is going to allow for the transesterification. You've got to use this as in a solvent. This itself would be a salt. Maybe it's a sodium ethoxide, for example. That's going to be a salt, a solid species. You need a solvent, so choose the solvent alcohol that looks just like the ethoxide. That's always going to be the best choice. This is, again, an example of a transesterification, only it's run under basic conditions. Mechanistically, the top reaction under acidic conditions is identical to a Fischer esterification. This one is going to be a nucleophilic addition elimination reaction. Let's go ahead and look at the mechanism for that one, see how it would work. So we're going to go ahead and we're going to start with this methyl ester. and we're going to add the ethoxide. We're in ethanol solvent, but we're adding ethoxide. Here we go. The nucleophilic electrons come in and attack the electrophilic carbon in order to form a tetrahedral intermediate, same as always. There's my tetrahedral intermediate. Now at this point, we can see I've started with an ester, and so I don't have a great leaving group on board like I did when I started with an acid chloride or even an anhydride. So if I'm going to reform the carbon-oxygen pi bond, I'm going to have to kick off an alkoxide, which is not necessarily a great leaving group. If I kick off the ethoxide, I'm just right back to where I started. There won't be much preference for that over kicking off the methoxide. You'd expect about a 50-50 ratio here in terms of what gets kicked off. But if I kick off the ethoxide, I'm right back to where I started. Presumably I've got a large excess of ethoxide, so it's not going to be too long before I'm right back here to this same tetrahedral intermediate. Every once in a while I will kick off the methoxide, and when I do that, I get my new ester structure. Why would the equilibrium favor this side? Well, again, I'm going to have to play with the Chatelier's principle, make sure that I have a large excess of ethanol and ethoxide, and therefore not very much methoxide to drive the reaction back in the other direction, at least not very much methoxide compared to the ethoxide that I add. So there it is, a transesterification, and it can be quite useful, particularly if you're trying to tweak the structure of the ester. All right, another reaction involving esters that I want to quickly review for you is saponification. We actually talked about this in the last chapter, the carboxylic acid chapter. Here I have 1, 2, 3, 4, 5, 6. This is the ethyl ester of hexanoic acid, or ethyl hexanoate. And a saponification reaction is one in which you treat that with base, namely hydroxide. This reaction is not catalytic, as it turns out. Saponification is not a catalytic process. It requires a full equivalent of ethoxide. But we can understand how it's happening here. We are going to produce a tetrahedral intermediate. And at this point, the tetrahedral intermediate can attempt to reform the carbon-oxygen pi bond. It's going to have to kick off a leaving group. I've got two choices. One is an ethoxide, which is not a great leaving group, and one is a hydroxide, which is not a great leaving group. Neither one of those is a great leaving group. But if I have an excess of hydroxide and water, which is probably what I would have under saponification conditions, then in all likelihood I could drive the equilibrium in the direction I'm interested, which would be 1, 2, 3, 4, 5, 6, which would be this direction. That's saponification. Notice that you're producing a carboxylic acid under these saponification conditions, but that's not going to last very long. The acid itself is quite acidic. Anything basic, including the ethoxide you just made, or more of that hydroxide which is present in excess, anything basic is going to pull off the acidic proton to give you this carboxylate anion, which is actually resonance delocalized. And it is this resonance delocalized carboxylate anion which can be soap. Now this particular one I drew has only got a 6-carbon chain on it, actually only a 5-carbon chain away from the carboxylate anion. So it's not going to be a very good soap. You need a larger chain in order to form those micelles that I talked about previously. But that's the saponification reaction, and now we can understand it in terms of a nucleophilic addition elimination. You can also understand why it's not necessarily as fast a reaction as with an acid chloride, because when we get to the tetrahedral intermediate stage, we don't have a good leaving group. It's going to be a slower reaction. It's going to require more severe conditions. If this were an acid chloride, we wouldn't even need hydroxide. We could just dump in water, and the reaction would probably be over in a blink of an eye. But with an ester, we're going to need this strong nucleophilic hydroxide present, and not a catalytic amount. We're going to need a stoichiometric amount, and we're probably going to need higher temperatures, more harsh reaction conditions. But we can get the job done and make these soap-like compounds, these carboxylate anions with long hydrocarbon tails in this way. Okay, so we've looked at transesterifications. We've looked at saponification. Still looking at reactions of esters, I want to look at the reaction between esters and organometallics. So we're continuing with the reactions of esters, and we're going to look at addition of organometallics. So let me go ahead and put an ester on the board. I'll choose that same ester I used a few moments ago. This is the methyl ester of benzoic acid, and I'm going to react it with an organometallic. Let me go ahead and choose a methyl Grignard reagent, methyl magnesium bromide. Well, when we looked at organometallics reacting with acid chlorides, what we found is that it was really tough to stop them from adding more than once. We're going to find the exact same thing is true with esters. Here comes the first addition of our organometallic in order to form a tetrahedral intermediate. There's my tetrahedral intermediate. The counter cation is just hanging out as a spectator ion. There it is. Now I can reform the carbon-oxygen pi bond. I don't have a great leaving group, but at least I have one which is can act as a leaving group. It's not the methyl, it's not the phenyl. They're not ever going to be leaving groups. It's this methoxide. Again, it's not a great leaving group, but given enough time and opportunity and maybe a strong enough kick in the pants, a little bit higher temperatures, I can get this thing to go. Once it's gone and you've made this ketone, the ketone will, just as in the case of the acid chloride, be every bit as susceptible to addition of another Grignard reagent as it was in the case of the acid chloride reaction. For this reason, just like in the case of the acid chloride reaction, you don't try to stop at the ketone stage. You will only be minimally successful at doing that. Instead, you use two or more equivalents of the corresponding organometallic that you started with. The second equivalent now is going to come in to form a new tetrahedral intermediate. You've now successfully added two methyl groups to that ester carbonyl. The second tetrahedral intermediate is different than the first because there's absolutely no leaving group on board here, and so it has to hang out and wait until you provide for a separate second step, namely a water H3O plus quench, in order to give the final product. And the final product is a tertiary alcohol. So this reaction, I hope, looks eerily familiar to you. It is exactly the same reaction we saw with acid chlorides. You should expect, and you'd be correct, that this is going to be a slower reaction than it is with acid chlorides because the ester doesn't have nearly as strong a leaving group, but you can still get it to go. And you can get it to go all the way to the tertiary alcohol, just like the acid chloride did. Organometallics adding to esters will give tertiary alcohols. Well, one more reaction of esters I need to show you, and then we'll be done with esters, and it is the reaction with metal hydrides. And since I've just shown you the reaction with organometallics and talked about the similarities that you saw with acid chlorides, let's review very quickly here. When we started with an acid chloride and treated it with two equivalents of an organometallic, like an organolithium, followed by a water H3O plus quench, we were able to convert it into the corresponding tertiary alcohol in which the two organometallics have added there and there. Likewise, when we started with an ester, we could do exactly the same thing. So in other words, we can get to exactly the same spot using, in the first step, an organometallic. Since I showed an organolithium there, I'll show a Grignard reagent here. We're still going to need two equivalents. In the second step, H2O, H3O plus, and boom, I get to the same spot. This is the slower version of that reaction. So that's what we've just recently discovered, that there's a lot of similarities there. Well, I want you to go back into your notes or into your brain and recall that if you treat the acid chloride with lithium aluminum hydride in the first step, followed by H2O, H3O plus in the second step, then you can convert this into the corresponding primary alcohol. So we make tertiary alcohol over here, and we can make primary alcohol using lithium aluminum hydride. Not surprisingly, if you start with the corresponding ester, you can get to the exact same spot. Once again, similarities between the acid chloride and the ester. It's just one is more reactive than the other, but the same set of reagents takes you to the primary alcohol. Well, if you remember all that, then hopefully you also remember that it was possible to take that acid chloride and reduce it to an aldehyde and have the reaction stop there. We can stop the reduction at the aldehyde stage, and the way we did that was either a Rosenmund reduction, which was hydrogen in the presence of palladium and quinoline, quinoline acting as the poison to give us the corresponding aldehyde. Or a second method was to use the tri-T-butoxy aluminum hydride as the lithium salt. So a lithium tri-T-butoxy aluminum hydride, which would also stop at the aldehyde stage. Given the similarities I've been showing you between the reactions of acid chlorides and esters, I hope it doesn't surprise you that we can, in fact, do a very similar thing starting with an ester. And I just choose the methyl ester of benzoic acid here as an example. We can go to the aldehyde. We can reduce all the way to the aldehyde and then have the reaction stop there. I shouldn't say all the way. We can reduce to the aldehyde and then have the reaction stop there. We won't use these reagents though. In order to affect this selective reduction and have the reaction stop at the aldehyde, starting with an ester, we need a new reagent which is called dibol. It's generally drawn this way, dibol H. What's dibol? Dibol is di-isobutyl aluminum hydride. So it is an aluminum hydride, just like this tri-T-butoxy aluminum hydride, but it's a different one. It looks like this. And you know what? I think I've given you the wrong structure. That would be di-sec-butyl aluminum hydride. Di-isobutyl aluminum hydride looks like this. There we go. There's di-isobutyl aluminum hydride. Di-isobutyl aluminum hydride is an aluminum hydride, but it's just a less active aluminum hydride. You can see that the isobutyl groups are fairly large. There's only 3 bonds on aluminum here. It's not this negatively charged aluminum hydride like we had here. or like we have with lithium aluminum hydride. It's just a reduced reactivity version of lithium aluminum hydride. And it allows us to stop at the aldehyde stage. So there you have it. Esters can go to the aldehyde using dibol H. You don't have to draw out the structure, just write dibol H and that's fine. Okay, so a lot of similarities between acid chlorides and esters. What have we done here? We've looked at the various reactions of carboxylic acid chlorides, a little bit with anhydrides. We've looked at esters, and there's only one species left that we need to talk about, and that will be the corresponding nitriles. So we're going to go ahead and finally look at reactions of nitriles. I started this discussion telling you that we were going to talk about all the different carboxylic acid derivatives, and that the nitriles, which look something like this, don't look a whole lot like the carboxylic acid derivatives, but they behave like them. Chemically speaking, they're definitely quite similar, and there are multiple tie-ins to carboxylic acid derivatives. Well, before I show you the chemistry of the nitriles, let me make sure we understand how to make them. This goes all the way back into Organic Chemistry 1. For example, if we had a species like this, this would be a 2-iodobutane. In this particular case, there's a stereogenic center, which happens to be R. So this would be R, 2-iodobutane. And I were to try to run an SN2 reaction involving the really good nucleophile cyanide anion, the nucleophile would come from the back of the carbon-leaving group bond, as always, in an SN2 reaction, in order to produce the corresponding S derivative. In other words, it is a stereospecific reaction. There is 100% inversion of configuration in an SN2 process. Well, that's one way to make organonitriles. It's not the only way, but it's a very convenient way to make organonitriles. What we want to do now is we want to investigate the chemistry of the organonitriles, and I think the first reaction I'll show you will simply be hydrogenation. Imagine, if you will, that were not a carbon-nitrogen triple bond, but a carbon-carbon triple bond, part of an alkyne. You've seen this reaction already. Hydrogenation, hydrogen in the presence of a transition metal catalyst. For an alkyne, that would hydrogenate the first pi bond to make an alkene, and then hydrogenate the second pi bond to make the alkane. The same thing will happen here. You will fully hydrogenate this from the nitrile all the way to the amine. What I've done is I've added 2 equivalents of hydrogen across those 2 pi bonds, and I now have an amine. So a very convenient way to make primary amines is to simply hydrogenate nitriles. That's an important reaction. Turns out you can hydrolyze nitriles as well under either acidic or basic conditions, but it is fairly well known that acidic hydrolysis of nitriles is much more effective and efficient. So I would recommend you always use the acidic version of the nitrile hydrolysis reaction. And what you will do is you will convert the nitrile into the corresponding carboxylic acid. This is a hydrolysis which will convert the nitrile into the carboxylic acid. Let's go ahead and look at the mechanism for this reaction. So if I started with benzonitrile, which looks like that, and I treat this with H3O plus H2O conditions, what do I have? I have an acid. Now, recognize again that there is a lot of similarity between nitriles and carboxylic acid derivatives. If this were a carboxylic acid derivative, the very first thing we would do is protonate the carbonyl oxygen. We don't have a carbonyl oxygen in a nitrile, but we have this nitrogen which is similar to one. And that's going to be the very first thing we do here as well. Protonate the nitrile nitrogen. When we do that, we generate a very electrophilic carbon. That's what the protonated nitrile looks like. I can draw a resonance form in which I move those pi electrons onto nitrogen. And when I do that, the positive charge moves to carbon. This is completely analogous with carbonyl chemistry. You protonate the carbonyl oxygen, show the resonance form in which the charge actually exists to a large extent on carbon. It's exactly what we're doing here. Protonation of the nitrile nitrogen produces a super electrophilic carbon, just like in carboxylic acid derivatives. Well, what's that super electrophilic carbon going to react with? No doubt water. There's plenty of water around. Oops. When water adds in, you generate an oxonium ion, which is very typical. And we'll just go ahead and take another equivalent of water to give us this species here. Now this is an interesting looking species. Really what we have here is a disguised amide. So let me show you what I mean. If I were to continue this reaction by allowing it to react, allowing the molecule that I've just formed to react with another equivalent of H3O+, there that nitrogen can pick up another hydrogen. Watch what happens. I generate this iminium ion looking thing. I can move those pi electrons out there and draw a new resonance form for this. There's my new resonance form. And in fact, I can draw another resonance form. I can delocalize the charge out onto that oxygen.